Hello everyone. I have new space now. Isn't this great? I have a whiteboard. So we're starting a new chapter on magnetic fields. And I've already had a number of you complete the homework. That's wonderful. I've already had questions from a number of you. That's great. I'm tripping over tractor parts. That's not good. You know, we're getting through this, hopefully. I hope all y'all is doing okay. So if you remember, when we started with electric fields, we started with the historical bit. We started with the charges accumulating on things, and people noticed things were attracted. And people noticed this historically too. People noticed that certain bits of iron would stick to other bits of iron. They were attracted. And then there was some repulsion and some attraction. And you remember this from elementary school, is magnets probably have a north and a south. And there's a lot of deep graduate level stuff that gets you to the fact that there's always a north and a south. You can't split this up. If you split it into parts, each part gets its own north and a south. Now, what's going to happen is there's some magnetic field associated with this, and it follows along like that. And it goes from north to south. Magnetic fields always seem to start on a north and end on a south when they're generated by real materials. Later on, I'll tell you about magnetic fields generated by wires, and they don't have this requirement that they have to begin and end somewhere, like electric fields. But they have to make sense. They have to be kind of... The ultimate thing is that they're going to be loops. Every magnetic field is a loop, and there's a magnetic field in the material that closes the loop up. All magnetic fields are loops in some way. All right. So that's not really necessary right now. I just wanted, this is the elementary school stuff that you've seen before. What I want to get to is the operational bit, the stuff you need to do to solve problems. And we're going to look at some magnetic field. So I'm just going to draw in a magnetic field. And I have been drawing it in blue, so... All right, and so for historical reasons, right, we have the name of the thing is magnetic fields, and so we're going to call it, that's right, B. It's a vector, and it represents essentially a way of dealing with how the particle is going to move. And you might think, oh, well, a particle that we put in here, positive charges will go that way, negative will go. It doesn't. All right, because here's what happens. If we set a charge in here, say we set a positive charge there, and we say V is 0, what we find is that there's no force on it. And that's a very unusual thing. That doesn't make a lot of sense for us. I just realized, went 4 minutes, and y'all can't see the rest of the board. I think you got the image, though. So, how's that? All right. So, now V is not 0. Then there's a force on it. So let's give it some direction here. And then we can go and ask, what is the force that this thing's going to feel? And obviously I don't have a third color marker for some reason. Here we go. Well, so remember, when we do into and out of the board, a circle with a dot is out of board. And a circle with an X is into. board. I have to be very careful not to do cursive here because I can tell it's not working. So this charge is going to feel some force, and the force depends on this velocity. It depends on this magnetic field, and it depends on this charge, Q. And what we're going to have is the direction is going to be into or out of the board. And if V is not equal to 0, then the force from the magnetic field is going to be QVB, the way it's set up now. And then we're going to put in that there's an angle phi in there. That's going to end up being sine of phi. So you had vector calc. This is cross product. We've talked about cross products before. F is QV cross B. And we talked about that when we did torque and when we did angular velocity, and we talked about a couple other places, I think. And so you need to remember your right-hand rules. And so I'm going to try to draw a right hand. I hope that came through good. Yes. So your book teaches you a particular way. Actually, I don't know if your book teaches this. The other book teaches this. You're going to have a velocity along the thumb. You're going to have the field along the fingers, and your force is going to push out. All right. So, right hand rule, thumb is upwards, your fingers are in the direction of the field, and you are pushing in the direction of the force. Now, I also told y'all once upon a time the physics gang sign. Right? Thumb is the velocity. First finger is the field. So what I'm showing you, velocity, field. And then this finger giving the bird to the force. It's out. In this case, it's toward the camera. And so this is basically what we're going to work with. This equation is the force that a magnetic field puts on a charge. If there's no charge, there's no force. If there's no angle here, sine of 0 is 0, sine of pi is 0. So if there's no charge, it's 0. If there's no angle, it's 0. And if the velocity is 0, it's 0. So you have to check and make sure if it makes sense. And that's why in the homework there's been a number of problems where what you had to do is go and sit down with the right-hand rule and say, well, the field is that way, and the velocity is up. So for this charge that I've drawn out, it is into the board. So we're going to let that pause for a moment, and we are going to try to solve some problems. Stop.